Okay, everyone, today we will run the first test cases for our introduction to microfluidic simulation. And now, can you see my screen? Sugar, can you see my screen? Yeah, okay. First of all, the first case is a channel flow. What is a channel flow? It means the flow.
No. Your screen is dark. In my pad, your screen is dark.
You can't see my screen.
Yeah, cannot see.
You can you see
Yeah.
my?
Now it's okay. Now it's okay.
Okay. The first test cases is a channel flow, which is a flows through a complex channel. First of all, we will see what the channel looks like, and here you can see the channel looks like, and it's very complex. And this is cater to our object, the microfluidic flow, microfluidic simulation. So the first thing we need to build up the geometry of this channel So I will give you some explanation of how to build this geometry and build this test cases. I would like to know, have you installed the SPHinXsys successfully and run some test cases by yourself? If yes, we will start this channel flow case. I have uploaded this test file into the Moodle and give some instruction to build by yourself. And in this lecture, I will lead you to build and run this test case step by step. Okay, the first of all, we need to build up the geometry of this channel. In this test case, we have two files. The point H file is the file to build up the geometry and the material and the body particles. And the second file is the point CPP file, which is the main file to run this simulation. First of all, we need to define the length and the height of this domain. You can see this is length multiplied by width. So we need to define the unit length of this domain is 1, and the height unit height of this domain is also 1. We will to define the geometry based on those parameters. And the resolution reference resolution is the distance between two particles, which means the neighboring particles distance. Yeah, this is a reference resolution. And this can be changed by yourself. If you use a smaller reference resolution, and you need to get more particles in this domain, and you will get more current results. But if you use a larger reference resolution, the number of particles is small, and the result is not very current. And the next one is sponge. Is the length of the sponge. This is the sponge region to impose the inflow condition. We know if we directly impose the inflow condition, it's not stable and may have some turbulence. But so we need to add a sponge region before the inflow. This will make our inflow more stable, and we can get more current results.
It's just the buffer thickness. The buffer contains 20 layers of the particles.
Yeah, I use a very large number to impose this inflow condition, and you can also choose your number to impose the inflow condition. It depends on your physical problems. And the next one is a boundary width, which this is the width of the boundary. We know the flow should have a boundary, and we define the width of the boundary is equals to the 5 times the reference resolution, which means, but in this case, it's not very apparent. And this is another parameter I will introduce later. These are 24 points we use to build up the geometry like this. And this is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4. Those are 24 points we need to build up the geometry of the channel. And these are four points I will introduce later. Now we know how what's the size of our domain. We need to build up a domain bounds of our computational domain, which should we should define these points, the upper left and the down left and upper right points, and we define a rectangle. This is a system domain bounds. We define the computational domain, what the size it is, and then we define the material.
Wait a moment, Bo. And this system domain is general rectangle shape, and the domain size should be at least more than the body size. You can choose the equal size and larger size than the body shape. Yeah.
Okay. Which means that the domain size is at least equal to our computational domain at least, and you can choose a larger domain size. And the next is a material property, and this is a material property to define the diffusion. In this our test cases, it not only has the flow but also the heat transfer in this test cases. In this snapshot, we can see the temperature distribution in this flow, and it has the heat exchange between the solid and the fluid. So we need to define the material property like the diffusion coefficient and the diffusion direction and so on. And the next, we need to define the material property of the fluid, which includes the density and the free stream velocity, which is also the inflow velocity, and the speed of sound, real number, and the dynamic viscosity. And those parameters, and you can change by yourself. And after my explanation, we will also change some parameters to see the different fluid velocity distribution and temperature distribution to see how those parameters affect the distribution of our flow. And this is
and moment, and the speed of the sound should be permanent because we simulate the weakly compressible fluid flow. So the speed of the sound should be set to 10 times the free stream velocity. Yeah, it should be not be changed. Yeah. Other parameters you can change by yourself, but the speed of the sound is permanent.
The next is the survey temperature, which means that in this case we have the uh, heat transfer, heat exchange between the fluid and the solid. So we have a survey temperature. I will show what the so we can see it has three different temperatures: the upper solid and the down solid, as well as the fluid has different temperature, which separate equals to the 10, 110, and 60. And the upper solid has a lower temperature, and the down solid has a higher temperature. The temperature of the flow is between them, and they can have the heat transfer during the flows through the channel. Okay, then we need to define the geometry of our body. The first body is our water channel, which means which is like this. This is this is a channel body. We define the domain of the water. We use the point we just defined before to create the water channel shape. And this is a function which returns to the vector type, and we use it later. This build up the water channel.
And everybody should pay attention to it. The beginning point and the ending point should be same.
Then we need to define the outer wall shape. Why it should be an outer wall shape like this? We can just define the rectangle like whole rectangle, but we need also to minus the water channel body. So we need to define the outer wall body and the inner wall body, and to the outer wall body minus the inner wall body, we can get the wall boundary. And here I write two different types to define the outer wall body, and I just use this simple method, and you can use this more complex method by yourself and to see what's different between them. But when you use the first method, you need to comment the second method. And this is outer wall shape. Here I define the rectangle of the solid wall. Then I define an inner wall shape. This is much likely to the water channel block. But pay attention to that. You need to be larger to the water block, which means that you need to have some domain extend the outer wall shape. You need to define like this, and you can use the outer wall.
Because we use the Boolean operation to get a complex body shape. So when we use the Boolean operation, the different body shape their sizes should be different. For example, the inner channel shape, the length in x-axis should be bigger than the rectangle length.
So this we define an inner wall shape, and then we can use the outer wall shape and the inner wall shape to build the wall boundary. And here we define a inflow buffer shape. This is also, I have mentioned before, the distance of the sponge. In this inflow buffer shape, we can to buffer the inflow boundary condition to make it more stable and steady. So we use it to post the inflow condition. And now we define the four body which separates the water channel shape, outer wall shape, and the inner wall shape, as well as the inflow buffer shape. And but those are all define the points, define the shape. We didn't build up the body. Now we start to define the body. In our code, there are 7 different types of body: the fluid body, solid body, and some other types of body. We need to define the water block from the fluid body, and we define the water channel by use the bool operation.
We use the Boolean operation.
Yeah, we use a Boolean operation, but you can see we add many circles. Why this is? It's a circle in the corner. If we don't add this circle, it's a straight. It's very straight, and it's not friendly to the flow to flow through. So we add the circle corner at each corner, and we can see it's more smooth. And we use this method to define. It's very complex, but you can try it by yourself to use this Boolean operation, and you can build many other geometries. Now we use the circle assistance and the insert circle reduce. We have leave it in the beginning, and we use it here to build the circle corner. And then we need to define the solid wall. Solid wall is a type of the solid body, so we use a solid body to define solid wall. And we also use the Boolean operation to build up those solid body. And we use the same method to build up the circle corner, but it's a different Boolean operation from the water channel, and you can see what's difference between them, and you can change the methods of Boolean operation and to see what difference they are. And now we define the water channel block as well as the solid wall block, which are these are our solid wall block, and these are our water channel block. And we also need to build up inflow buffer region. I would like to mention is that this inflow buffer region is not it will be not changed during our simulation. It's a fixed particles in this region, and it will not exchange with the flow part, and it's just impose inflow velocity and the boundary conditions to our water channel. And then we need to define the heat conduction material properties. Because our case also includes the diffusion properties, so we need to define the diffusion property, and this is a class to define the water materials diffusion property, and this is a class to define the solid materials property. And because diffusion is not the main object for our lecture, and I will leave it out here, and you can to explore it by yourself. And this is a thermal solid boundary initial condition. We define the initial condition of our solid wall, and we use a different range and to define the initial temperature of the solid wall. And these are defined the lower wall in initial temperature, and these are define the upper wall initial temperature. And we also need to define the fluid boundary, fluid body initial temperature. So we also use the same method to define the fluid initial temperature, and the temperature are defined. And this is a dynamic diffusion dynamics between the fluid and the solid. We define here, and we will use it as a main file to simulate the heat exchange between the fluid and the solid. And this class is inflow boundary condition. We use the parabolic shape inflow boundary condition, and we use this function to impose initial velocity. So the profile of the initial velocity is parabolic, and this will be more friendly to our simulation.
And wait a moment, Bo. And this inflow velocity setting, and because it's a parabolic inflow, so the velocity in y direction is always 0, and we just change the velocity in x direction. And this setting process includes 2 steps. The first step is the class setup dynamics by time. The velocity will be accelerated according to this algorithm by time, and then in the class get target velocity, we modify the inflow velocity by their position. So after these 2 steps, a final velocity will obtained by us here.
Okay, and the last step of our build file is the observer. What is the observer? When we simulate, we not only want to know the those counter and how the whole flow change by time. We also want to know some points the value to vary from the time. So we define some observer, like in this case, we define we define 10 observer points in each opposite corners, and like this one, this, and this, and we observe the temperature and the velocity during our simulation, and we can to plot the temperature and the velocity here of the observed points varied runtime. So this is the points H file. We defined the case body material and some other parameters will be used in our simulation. Actually, you can also put this file in the point.cpp file, but it will it will be too long for complex case. So I suggest you separate the different type code into different file. Okay, we will start the second file, point.cpp file, which we include the case build up part, and we can use everything we defined here in our main function. Okay, for our main function, the first thing is that we need to build up a SPH system, which includes many things and will be used in our simulation. It's like for each case we need to build up a system and to define some parameters and some characteristics related to our case. And actually, the system parameter of the build up function parameter only include the system domain bounds and the resolution reference, and the other build function parameters are default to some value, and you can also change them here. And we need to define the global static variable, which is a physical time. So we start from the physical time 0 and to conduct a simulation. Okay, the next one is the system, the particle relaxation. This is a very important part for some cases, include the non-square or rectangle geometries. For example, we use a circle or some other geometries. This part is very important for us. So I would like to explain what is a particle relaxation. So I will show you this domain, and this is and this is also a domain. And first, I will tell you what we generate the particle. We use the mesh background mesh to generate the particles, and we separate the computational domain in x direction and y direction into a very small cell. And in each cell, we put a particle, and we generate the particle of this body. But we can see in the corner, the particles are not very close to our body profile. From our definition, we know here is a circle corner, but from the particle it looks like it's different from the shape of the circle corner. So we need to conduct the particle relaxation to let the particle more close to our geometry profile. So how to conduct this particle relaxation? I will show you how it changed. wait for a moment. We can see how is change more smooth to the geometry profile, and this is a non-relaxation particle distribution, and we can see its roof in the circle corner. It's not a current for our simulation, but after the particle relaxation, it is more close to the geometry profile, and this will be more conducive to our simulation. The results will be more current. So the particle relaxation is very important for some non-rectangle or non-square geometry profile. And so when we set the round particle relaxation true, and the simulation will first run the particle relaxation to relax the particle, and after we get the run particle relaxation, we could get a folder called reload. Yeah, after we run the particle relaxation, we can get a folder called reload, and it has XML file which defines the relaxation, relaxed particle distribution, and we set the reload particle equals to true, and it will read this file and to set the initial particle distribution at the relaxed state. And this is particle relaxation, and here is the process of particle relaxation, and I will not give you detailed explanation of how it's relaxed, and you just need to know when we encounter some non-rectangle or non-square geometry profile, we need to relax the particle distribution to make it more close to our geometry profile, and you can reference this method to relax our particle. And then we define we define the material and body as well as the particles in our build up file, but they are they just class in the CPP language. Now we need to give its parameters to have our own objects. For example, we define the water channel before. We define the water channel before here in the, but it's just a class. We define a class, and we define our object here with our parameter. Yeah, we define a new object for our for current simulating case. And we also define the water material as well as a particle. For our simulation, we need for each body, if this body is involved in the simulation, I mean it's exchanged parameters or characteristics with other bodies. We need to define three things. The first is a body. We define the water channel body, and the second is a material, and the third one is a particle. The definition of the particle is based on our definition of body and material. We define the water channel and the water material, and we use the water channel as well as the water material to define the fluid particles. And the solid wall is also is the same as the water channel, because we exchange the heat between the fluid and the solid. So we also need to define three things for our solid wall: the solid wall body and the solid wall solid material, and as well as the solid particles. In the current case, the solid and the water and the fluid parts are same definition method. Then we need also to define the observer part. We know the observer don't exchange the parameter or characteristics with the water channel part. It just got some values from the water channel. It doesn't have interaction with neither water channel or the solid wall. So we don't need to define the material of the fluid observer.
The observer particle is not a real particle, so we don't need to define it as the solid particles or water fluid particles. Yeah, because this is because why we need to add the observer, because sometimes we need to output the data in a specific point, so we need to add an observer. Yeah.
Actually, in our statistics, there are two different types of body. One is a real body and fiction body, and the other, and we also have two different particles. If this particle don't have interaction with other bodies, we define its fiction particles, and we don't need to define its material because it doesn't have interactions with other other particles or bodies. And up to now, we have defined what we need in our case. They include the water channel and the solid wall as well as our fluid observer. Then we need to define some other things. For example, we need to define the input-output. The input-output class is also a base
it's a base class for the input and output data.
It's a base element for other input-output functions. For example, here we define three different type of input-output function. The first one is the write restart. Use this in input-output function. For example, when you simulate a case and you are diverged at some time, but after you try again, you don't want to from the zero time, and you can start from a specific time, and you can reload the restart file to restart your simulation from a specific time, not from the zero time, and this is to repeat to resimulate your cases from a specific time. And the second function is read restart. This is combined with the write restart. One is to output the restart file, and the read restart is to read the restart file from your folder. Yeah, we have a restart folder, and now it's empty because but if you define write restart file in your simulation, and you can get some cell separately in specific time. And the third function is the write body state to VTU file, and this function can allows you to output the counter, yeah, like this, the counter in different times in different snapshots, and you can use the parallel or tag plot to visualize them. Here we use the VTU field, and it can be loaded by the parallel software, and you can also change here to PLT if you use the tag plot to visualization. So you can try different
write
methods.
body states to PLT. There should be two.
Yeah, you can also use a PLT field to visualize user tag plots. It depends your choice whether you are familiar with the parallel or tag plot. It's also both okay. We use the VTU here, and because we use the parallel to visualization. And then this is the body topology. This is a very important part in our simulation. It defines the interaction. It defines the relationship between different body and the body itself. For example, we define an inner body relation. In the fluid body inner, which means that for our fluid body, one particle in fluid, it has interaction with its neighbor particle, but all of those neighbor particles are belonging to the fluid body. So we define a fluid body inner. This is a relationship within the water channel body. And we also define a solid body inner. It's a theme. It's a relationship within the solid body and solid wall body. And the third one is a complex body relationship. We know the fluid particle, such as in the boundary. For example, the fluid particle in the boundary, its neighbor not only has the fluid particle but also the solid particle. So it has two different contact particles. So we here define a complex body relationship. It includes the inner body relationship. The fluid particle interact with the fluid particle is inner body relationship, and it also has the relation contacting with the solid particle. This is a contact body relationship, and the complex body relationship includes the inner body relationship as well as the contact body relationship. And the last one is the contact body relationship. This is specific for the fluid observer. For example, we have observed the point here, and this observer particle has a relationship with the fluid particle, and it's not has inner body relationship. So we just need the contact body relationship for observed particle with the fluid particle. So those are three different kinds of relationship in our SPHinXsys code, and you can analyze your own cases and to analyze what's the relationship between different bodies and different particle types. Okay, this is the method to conduct the particle relaxation, and we will leave it here. And you can, if you have interest in, you can analyze the detailed it by yourself. And then we start the method and the dynamics part for our simulation. And first of all, we define the thermo-solid and as well as thermo-fluid body initial condition. In our build up file, we define a class called thermo-solid body initial condition, as well as a thermo-fluid body initial condition. But they are just the definition of class. We need to define our objects with our body here. We define the thermo-solid condition. This is object of the thermo-solid body initial condition class with the solid word specific for this thermo-solid condition. In the same method, we use the water channel body to define the thermofluid initial condition, and this is also a object for our thermofluid body initial condition. Here we define two objects for our simulation. Then we define several other methods and objects for our simulation. For example, we define a character configuration as well as some fluid dynamics part updated density by summation, as well as other some methods. And when we actually the order of this definition it doesn't matter. You can define the fluid dynamics part in the beginning, or some other methods in the beginning. The order it doesn't matter. But
the first four classes is just for the initial condition setting, yeah, and the fifth class periodical condition in axis direction using cell linked list is used for update the background grades. Because in the flow process, the particles will flow through the grid. So we need so in each time step, different particles will be included in the grids. So we need to update the particles in a specific grid. So this class is used to update the grids in the background grids.
And when we define all of those methods, we need to include related all of related methods here. If you have got some method definition here, the results will be not very current, or the result will be wrong. So you need to define all of the related methods here. And we will continue to explain the method. We need to initialize a timestamp. This is for the fluid step, because in the current case, only the fluid has only the fluid particle has a movement, and it will be changed by time, and we need to initialize a timestamp for the first sample. And the periodical condition in x direction using cell linked list. This is if you are very familiar with the computational fluid dynamics, you must know the boundaries and the periodic boundary condition. And this method is to impose the periodic condition. For our case, actually, we have a periodic condition in the x direction. The outflow and inflow are periodic, so we define a periodic condition here. You can also define the periodic condition in the y direction or z direction, and you just change you need to just change here to 1 for the y direction and 2 for the z direction, and if we use 0, it is for x direction. And the density summation complex. This is update the density by summation. This is related to the methods of the SPH, and it's update the density after one time step. Yeah, this is the aim for this method. And then we have two different time steps. One called the advention time step, and another is called the acrostic time step. And actually, this is algorithm to let the simulation more current. And I think for our lecture, you don't know much more about why it should have 2 timestamps, and you just need to know when we simulate, we need to define a timestamp, and we calculate the parameters and flow field stamp by stamp with the timestamp. And for this case, we also include the diffusion. So we need to also define a thermal timestamp. This may be smaller than the fluid flow timestamp. It is a advention timestamp as well as the acrostic timestamp. So when we have several time steps, we need to choose the smallest time step to forward the computation. If we use we use a larger one, the field related to a smaller time step will be not in current and will be wrong. And this is a thermal reaction complex. It's the same. It's the same as the fluid relation with the solid. But when we refer to the relation between the fluid and the solid, we just referred to the focus and some other parameters related to this relation. But for the thermal relation, we need to refer the temperature interaction between the fluid and the solid. So we defined the thermal relation separately to define this thermal relaxation complex. And here are 5 different fluid dynamics methods. I think we need to just to use it. And
the first class pressure relaxation with O is used to update the pressure.
We don't need to know much about for those methods. And for our lecture, we just need to use it. That's enough.
Okay.
And this is a parabolic inflow. This is define our inflow boundary condition, and we use the inflow buffer. We defined in our build-up file. And those are all methods will be used in our current simulation. But it's not, and we also we have other methods. For example, we need to define the observation method. As I said before, we observed the temperature and the velocity in the observed point. So we defined the 2 observer methods here. One is the right fluid velocity, and the other one is the right fluid temperature to observe the temperature and the velocity of the observed point. Okay, up to now, the methods we used for our simulation all defined. And the next is and the next part is the reload particle. This is
if you use the restart function, this
no. This is not a restart. This is a relaxation.
Oh, for the relaxation.
Yeah. If you set the reload particle equals to true, you want to reload the relaxed particle from the reload file, and you will use this part to reload the particles from the file to build up the initial particle distribution at the relaxed state. And this is a reload particle part. But if you still just want to use the unrelaxed particle like this to conduct a simulation, that's no problem. You just to set the reload particles to false, and it will not reload.
Ground particle relaxation should be set to false too.
No, it doesn't matter. It's two separate things. Yeah.
Okay.
Oh yeah, you mean the second wrong. Yeah. Shogo is right. You need to set the run particle relaxation and reload particles equals to false, and you can use this unrelaxed particle to conduct a simulation. That's no problem, but the result is not guaranteed. Okay. And we defined the method. We defined the method in this part here. And now we need to use this method. In each method, it has interface to allows us to use it during the simulation. And before the simulation, we need to use this method. For example, we need to use the system to initialize the system cell-link list. This is an interface defined in the class SPH system, as well as we need to build up the initial boundary conditions, as well as the thermal solid condition, and those methods we need to use them before we simulation, and you just need to use it. So that's enough. And here we calculate the timestamp of our thermal diffusion. Okay.
This is because some parameters have long values at the beginning time, so we need to execute these functions before the beginning of the simulation to give the initial value to some parameters. Okay, you can continue.
Okay, the next part is restart step. This is to our restart a new simulation, not from the 0 time, but from a specific time. And if you want to do this, you can use this method to restart the simulation. And here before we start the simulation, we will write the initial state of our body. Yeah, that is this one, and this is the initial state of our fluid and solid body, and then we define some parameters will be used in our simulation, such as some restart output interval and screen output interval, and some end time is the total simulation time for our case, and the d time dt, small dt, and inner iteration dt. These are some parameters.
The d time is used to output the data, such as the VTU file or PLT file. In every d time, the data will be output.
Okay, now after we define those parameters, we will start our main loop. And in the main loop, we need to
there are 2 for loops, and in every for loop, we should to execute different class. So you can see here, this is the details about the details to execute the class.
Yeah, as we have mentioned before, we have two different timestamp. One is the advention timestamp, and another is the acrostic timestamp. So, so the fluid methods are matched with different within the different timestamp. For example, when we calculate the advention timestamp, we need to update the density by summation and viscous acceleration and transport velocity correction. And actually, in generally, the acrostic time step will be smaller than the advention time step, and the advention time step is several times of the acrostic time step. So we need to run several. We need to simulate several acrostic time step in within advention time step. But in this case, we also mentioned thermal time step. So we need to compare which time step is the smallest. We need to run it, and we need to match the methods within this time step. In the acrostic time step, we need to conduct the pressure relaxation, density relaxation, and thermal relaxation complex. And those are matched with our acrostic or thermal time step. But the advention time step is larger. We just need to update the density by summation and viscous acceleration and transport velocity correction. And we also count the number of the iteration in iteration by this number of iterations. If this encounters encounters the value we have set here, for example, the screen output interval or restart output interval, we will output something to our screen or to the output folder or restart folder. And after each advention time step, we need to reset the parabolic condition, and water channel should be updated the cell link list and the configuration. What is the configuration? Because, for example, for a specific particle, it has a neighbor in this circle, in a circle. But after it's run sometimes times its neighbor will be changed. So after each advention time step, we need to update the cell link list and the particle configuration. This is used for the next advention time step. And after D time is the time steps for output. If for each output time step, we will output the real body state and temperature, as well as the velocity observed data into our output folder. And so
yeah, and this output, the data output by these three functions will be stored in the VTU file or PLT file.
Yeah, the right real body state is objective of the right body state to PLT or VTU, and it has interface right to file. This will allow us to write the current observed data to the file, to the PLT file or VTU file. And this is a main loop for our simulation, and it has several circles, and the last thing is some definition to let us know how long we have used for simulate for our this case. And this is a whole process to build one test case. And I would like to know, have you installed the SPHinXsys?
But in here we have in total we have 2 files. The first is .h file, yeah, and the .cpp file. I think all students can do the operation only in the .h file, and they don't need to care about the parameter settings in the CPP file.
Yeah. If you want to do some modification parameters, you don't need to change some parameters defined in the .h file, and you can rerun.
Yeah. Okay. They only need to learn how to change the geometry about the different body shapes and the flow parameters, such as the velocity and the heat transfer. So they all the modification by them should only be operated in the H file. Yeah.
Okay. So I would like to know if you have some questions related to this channel flow case, and if you haven't installed the SPHinXsys, if you encounter some problems when you install the SPHinXsys, and you can let me know, and we can discuss it here.
If we will wait for about 3 minutes. If you have any question, you can ask us online directly. If you don't have the questions, you can this class will be ended.